This is Darif Sites. This video is about algorithms flow control. Algorithms define processes, which are sets of instructions that are carried out or executed in a particular order depending on current conditions in the environment. Flow control specifies an algorithm's execution flow as it's carried out by a computing agent, whether it be a computing device or a human. Here in this picture we see train tracks, and notice the various branchings that occur and possibly some loops that are happening so the trains can go at certain places every day. So this is a good analogy of the concept of flow control. In algorithms, there are flow control mechanisms that allow branching and looping and straight line progress. There are 6 flow control types. The first, the most basic, the default flow, is sequential. Each statement executes one after another in a straight line manner from top to bottom in the text pseudocode that defines an algorithm. A variant of sequential is call and return, where instead of a single statement, an entire block is referenced by the concept of moving it somewhere else, separate, in an organized manner, in a modular manner, and delegating, instead of that statement, the work to be done in this separate flow. When that separate functionality is complete, flow returns back to the mainline flow from where it was called. That's why we call and then return to that point. The next type of flow is selection flow, which allows branching based on conditions. It's also called conditional flow. And in selection, one of 2 alternate blocks are executed, or more than 2 blocks in certain cases, based on a Boolean condition. Boolean is a true or a false condition. Repetition flows, also known as looping or iteration, allow for a specific block of code to be repeated. The number of times can be based on a variable or a condition. More advanced flows are simultaneous flow, also known as concurrent or parallel processing, where multiple statements execute at the same time. This kind of flow requires usually a multiprocessor environment. And another advanced flow, a wait flow, which waits for a certain event to occur, which may be a certain time duration occurs, or some other environmental event occurs, and there's a pause or delay that takes place until that event happens. We will now look at each of these individually. Sequential flow, the default, begins at the top of the algorithm and proceeds down statement by statement. Straight line flow, like a single railroad track with no branches in it. An example, the pound sign here is a comment. Calculate and output the sum of 2 numbers. 4 statements. First, get first number. First number is a variable. Variables are needed in algorithms to hold values that can be evaluated. They can be used in conditional tests. So get first number, or they can be used in calculations. Get second number from the environment, and then set the variable sum to the mathematical sum of those two numbers, and print sum. 3 variables used, 4 statements. From top all the way down, straight line, sequential flow. Call return flow. On the left here, the main flow. Notice that this one statement here is a call to a function called M. M standing for something that's modular, off to the side somewhere. And function M does its job, whatever it is. It was delegated that work, and when it's done, it reports back to the mainline flow, and the result of that work has been completed. If there's an answer that was requested, that value will be returned right to that statement at that point. And then flow continues with the next statement sequentially up to that. An example comment here says calculate and output the square root of a number. First, get number, then set answer, which is a variable, to square root of number. Square root is a function in a separate modular area of code, and that function requires a number to be sent to it as part of its call. That's called a parameter in parentheses here. It does its job and returns the square root to the point of call, which is then assigned as the new value of answer. And then flow continues sequentially, and the answer is printed out. Selection flow, also known as if-else, the most basic form of it, starts out with a condition. This diamond indicates a conditional test. A question is asked that has a true or a false answer. It involves a variable or more than one variable in the algorithm. If the answer is true, then the if branch of the flow, the statements that are indented under the if, are executed next. Otherwise, the else branch, the statements indented under the else branch, are executed next. Either this group or that group, which either one can be one or more statements. And then after one of those occurs, the next statement in the algorithm is executed. Here's an example. Determine and output whether a number is positive or negative. The first statement is sequential flow, just get the number. It's an input statement. Then here we have an if statement. If number, the value of that variable, is equal to 0, print neither positive nor negative and stop. Notice that these two statements are indented under this if. They will both be executed if number is equal to 0. Because 0 is neither positive nor negative, this answer would occur for that case. The stop statement immediately ends the entire algorithm. Nothing will happen after that. If the number is not 0, then we come down to this if-else construct. If number is greater than 0, print positive. That's what's indented under that statement. Else, print negative. Depending on number, this positive printing or this negative printing will occur. Repetition flow. again begins with a condition. Normally there's a variant of it where the condition can be at the end of the loop body. We're only looking at the primary while loop form here. So if the condition is true, a loop body, a block of statements, will be executed. Otherwise, that body will be skipped and the next statement in the algorithm will occur. After the loop body is executed, if the condition was true, the flow will return to the condition to check again. If it is still true, then the repetition will continue, and that loop body can be repeated multiple times depending on this condition. An example, determine and output the sum of a set of numbers. There's a variable total set to 0. From the external environment, we get next number of variable is obtained, and then here's the repetition, a while statement. These two statements, which are indented under the while, will be executed if next number was obtained. Notice that it's a set of numbers, and at some point it will end, and when that happens, there will be no next number obtained. But as long as there's one to get, we add next number to total, and then get next number again from the environment, the next one. This will continue until all the numbers have been obtained, added to the total, and then the total will be printed out in this next statement right here after the while loop. Simultaneous flow is a more advanced flow, a multiprocessor environment. We have statements executing on one processing device, one computing agent, and simultaneously another group of statements on another computing agent. Since this is an advanced flow, no more detail will be discussed about it in this video. The last flow, also an advanced flow, is a wait flow, where the algorithm stops and waits either for a certain time period to elapse or for a certain event to occur. And when this happens, and only then is the next block of statements executed. And frequently when dealing with events, the block that is executed varies for different events. Flow control, these basic constructs that we've reviewed, they can be nested, so they can have a richer combination and more complexity. These structures can be nested inside other flow control structures. For example, in the body of an if statement, in the if block, inside there, whatever those statements are, there could be other if else's inside there, or repetition statements in there, making it a more complex algorithm using nesting. As you get deeper into the nesting, the algorithm becomes more complicated to understand and maintain. Computer scientists must create flows that are as easy as possible to understand and yet still being efficient. Deeply nested flows should always be examined to try to simplify them and have fewer levels of nesting, because each additional level adds a lot of complexity and makes understanding more difficult. Finally, the use of delegation, or that is modularization of the code, and to functionally organize it into units, is the foundation of code readability and maintainability. Rather than having everything in sequential flow It's a good practice to identify common cohesive groups of code that can be functionally separated out or reused in different flows and called from those flows. This ends this introduction to algorithm flow control.